Hey biologists, Mr. Fott here. Today we're going to be going through chapter 4, talking about carbon and the molecular diversity of life. A little bit of biochemistry today. So first up is the must-knows. We're going to be talking about the properties of carbon that make it such a versatile and useful thing, especially for organic creatures such as ourselves. So first, let's talk about the importance of carbon in and of itself. Organic chemistry, this is definitely going to be a branch of chemistry that many of us are going to have to take in college, especially if you continue on and pursue into the life sciences. This is dealing with the chemistry specifically of carbon-based compounds. So thus the word organic in this reference actually means carbon-based, so carbon-based chemistry. Organic compounds, for instance, these are going to be, of course, just as organic chemistry is relating to carbon, organic compounds, they must have carbon at their core as well. We're going to be diving into some of the major elements of life that you may recall from standard bio are CHNOPS, or a fun alternative acronym could be PONCHOS, PONCHOS, can help us form these large, complex, and diverse molecules that make up the vast array of life. So let's talk about some of the things that make carbon so special. First up, it has 4 valence electrons. Keep in mind, to determine the number of valence electrons, you may recall from chemistry, it's going to be determined by the group A is what it's going to be, not the B with the transition metals as well as the lanthanides, actinides down below, just the A elements. So it's in group number 4, ergo it has 4 valence electrons, sometimes referred to as tetravalent. Another chemistry term there, that tetra referring to 4, much like the game Tetris, like the game with the falling blocks, which has 4 blocks in them. So what is special about being tetravalent or having 4 valence electrons is that it can form up to 4 different bonds, 4 being the max, not really above, not really below. It's got to have 4 pretty much all the time here. Some common bonding partners you're going to find are hydrogen, oxygen, and nitrogen, thus indicated by our PONCHOS, our ponchos, little acronym here representing the major elements that are going to be within life or organic chemistry. A few other things that it can do is that not just form 4 separate bonds, it can also form double bonds or even up to triple bonds as indicated in the diagram below. So we can see the double line, or it kind of looks like an equal. That's a double bond in which there are now 4 valence electrons being shared, or 2 per bond. Then we can also have a triple bond, such as the one on the far right, with the triple lines, again indicated 2 electrons per bond, saying that there are now 6 valence electrons that are then being shared. We are not going to go into 4 valence electrons or have a quadruplets. Those do not exist, at least in the organic chemistry realm, to my knowledge. So we're going to stop at 3. Sometimes also when we are doing things within the realm of carbon, these names might pop up. Notice how it's indicated in the diagram also, the endings. So the first one on the very far left is known as ethane, A-N-E. So when you have all single bonds, this is how you represent the ending of that molecule, is that it has an ane ending. When you have double bonds, you now change the ending to now say ethene. Again, the ene, the ending, represents that there is at least one, if not more, double bonds. Then again, when we change to triple bonds, we use ine, not wine, I guess, or however you else want to try and pronounce it. It's pronounced ine. So ethine would be the proper way to do this. These are generally referred to as alkanes for single bonds, alkenes for double bonds, and alkynes for our triple bonds. These may or may not pop up as we go through our class, so just as a frame of reference, if you're wondering how did they name things and where does the name actually come from, there is a lot of meaning behind it. We are not going to go into what's called IUPAC naming. That's more for organic chemistry. You can study that when you get to college. So a few things that these can do is we can form these macromolecules, macro meaning large, and molecules representing our organic compounds that we're going to be discussing. So we have 4 of them as major, as you again may recall from standard bio: carbohydrates, proteins, lipids, and nucleic acids. So we're going to be discussing the functions, how do we create these, how do we break these down, and what does our body actually use them for. So a simple overview would be of the 4 macromolecules, carbs, lipids, proteins, and nucleic acids. Here's a simple chart. So we can first indicate the elements. Notice how they all have CHO. Only proteins and nucleic acids are where they're going to deviate a little bit. Both of them do contain nitrogen, but one, the proteins, will contain sulfur, whereas the nucleic acids will instead house the phosphorus. Next, the monomers. So if we break this word apart, mono refers to one, mer means unit or building block. So the single unit, if you will, could be referred to as simple sugars in the case of carbohydrates, fatty acids and glycerols for lipids, amino acids for proteins, and nucleotides for our nucleic acids. The polymer, once again, breaking apart into its separate words, poly meaning many, mer meaning units, many units. So if we put a whole bunch of those monomers together, we can make a polymer. So for instance, we could have things like polysaccharide, poly meaning many, saccharide in this case representing sugar. And that's how you properly pronounce that is saccharide. It's a fancy Latin word for sugar. Next, we have lipids for our lipids category. That makes sense. Polypeptide for our proteins, and nucleic acid itself for the nucleic acids. A few examples of each of these are indicated in the last column. Starches and cellulose for carbohydrates, fats, oils, and waxes for lipids. Insulin is a great example for proteins, and DNA, or deoxyribonucleic acid, is a great example of nucleic acids. A few other special things that carbon can do. It can form not just single, double, triple bonds, but it can also form these long chains or branches. And as we start to investigate some of our macromolecules, we'll see these same structures will pop up time and time again. So these long, lengthy chains can be formed. We can also have different positions for the double bond. Now you might be thinking to yourself, does it matter? I mean, if it has a double bond, it's just going to do double bond things, right? And the answer is yes, it actually does matter dramatically. And we'll talk about that as we go through why very specific orientation of things, they do matter. We can also have branches down as indicated at the bottom left. So things will then produce branches, much like branches on a tree. Or last but not least, we can form rings or cyclic type structures. Additionally, what can happen is that we can form these things referred to as isomers. Iso meaning same, mer once again meaning unit. So look it down at the bottom. If we were to observe some of these, that they have the same chemical formula, C2H1, 2, 3, 4, 5, 6, H6O1. So it's the same exact chemical formula, however, they are going to be subtly different to one another. This is referred to as an isomer, where the formula is the same, but the structure or the way it is oriented in three-dimensional space, that is what's going to change. On the last side here on the right, these are referred to as enantiomers. This, a great example would be like, for instance, you or I, we might be left-handed, right-handed, or possibly even ambidextrous, where you're both left and right-handed as your dominant hand. Our chemicals can also be enantiomers, or they can have handedness, left-handed and right-handed. And depending on which orientation it is of the molecule, it will change things dramatically. A fantastic example, albeit very sad, is the example of a morning sickness medicine for women. It's referred to as thalidomide. And if you had the proper enantiomer, or if it is left-handed, it actually helps reduce morning sickness. However, if you have the incorrect enantiomer, you have the right-handedness, it actually caused all sorts of abnormalities and birth defects within the child. So this was actually the first discovered incidence in which we realized that they were what's called a racemic mix. You have a difference or a split 50-50 between when you created this substance, the thalidomide, 50% of it turned out to be left-handed and 50% of it turned out to be right-handed. And so this was kind of the birth of this understanding between handedness or enantiomers that exist between our molecules. Thank you all for listening. Let me know if you have any more questions.